So, like I mentioned earlier on, we are concluding integrals that have to do with trig expression. And to start with, I wanted us to look at an expression like this one. And the question is, how would you integrate something like this? Well, it turns out that something like this, sometimes every now and then, you get expressions such that to integrate those expressions, you first have to complete the square. We have looked at different expressions, especially the ones that have a square root. So if you see an expression, it has a square root. You really have to see the difference here. We are moving towards partial fractions. And when you see an expression like this, maybe instinctively, you want to say, okay, maybe I can express this as a partial fraction. Well, the difference between these and the examples we do under partial fractions is the presence of this square root here. That's the difference between this and what is coming next. But what if you have something like this one and you wanted to integrate it still? Well, it turns out that to actually integrate something like this, you would first have to complete the square. Now, what do I mean? Well, if you have an expression, let's say the argument here, this is x squared plus 2x. Yes, please.
I'm unable to see your screen.
Is it just him? Anyone else also having the same problem? Because I do have two devices connected. I'm able to see the screen on the other, so it should be fine, really. But just be very careful. There are two devices that I have connected, and they both have my name. So just make sure you have the right one pinned on your screen. Because one is sharing, the other one is not sharing. Zumil, are you able to see my screen?
Yeah.
Okay, so it should be should work. Okay, so what is happening here? So if I get the argument here and try to complete the square in this case, look at what happens. You guys know how we complete the square. You want to make sure that the argument, the coefficient of the x squared term here is 1. Once that is guaranteed, you want to focus on the coefficient of the x term. Get half of it, square it, add it, subtract it. So I have x squared here plus 2x. The coefficient here is 2, so I'll add it first. Then I'll get half of 2, which is 1, including its sign. It's positive, so I get positive 1. So half of 2 is 1. I'll square it. Then I've added there. Now I'll subtract it. So this is squared again. Now I'm subtracting. Then plus 4. This is how you complete the square, guys. Remember the steps. At this point, of course, you focus on this. You, in a way, just get the x here. Get the 1 from here, including the sign. So it becomes plus 1. And then square this. You know to say this 2x will somehow be taken care of by this expression here. So that's how it goes. Then from here, everything else that follows must be exactly the way it is. The square of 1 is going to be 1, then that is plus 4. So if this reduces, this becomes x plus 1, and then squared, then this becomes minus, not minus, plus 3. So we end up with this expression. So our integral, which was the integral of, we had 1 over all that. Now this is 1 over. I can rewrite it so that I start with 3 plus, and this is x plus 1 squared. X plus 1 squared. And of course, we have that integral here. So this is where we are now. And when you look at something like this, like where we are now here, you can easily say, of course, this is dx. At this point, you can easily say, let x plus 1 here, let this be equal to or be represented by a variable like u, so that now the integral becomes something like 1 over And then this becomes the integral of 3 plus u squared. And then, of course, if this is u, would need to get what du dx is, and then you'd differentiate this. Of course, this would just be equals to 1, and this would imply that dx would just be equals to du. So where there's dx here, I'll put du. So this is where we are now. Now this is what you'd have to integrate. Now what I wanted to point out here is you can have expressions that look like this. It has a square root, and you can't really get rid of that square root. If you try to take it to partial fractions, it might not work because of the presence of that square root. To integrate these, you might have to complete the square, and just as you have seen here, it reduces into two expressions where one is squared, the other one is not really squared, just a number. And look at how it reduces. It now reduces to the form that might actually look familiar to you. In this case, it reduces into a form that we haven't dealt with yet. It has reduced into a form where we have the square root of a number here. This is 3, and then we have plus u squared. The cases that we have dealt with, when this showed up, we know to say there was no square root here. Because there was no square root here, we used a tan substitution. That is what worked here. But in this case, because of this square root that is present here, a tan substitution would not really work here. Instead, would have to actually use substitution of hyperbolic functions, which we have not yet touched on. So I'll leave this here. But after we do hyperbolic substitutions, we're going to come back and see how you integrate this all the way to the end. But I just wanted to show you guys such that it's possible to get expressions, the ones we have been looking at so far, where when they give it to you, it doesn't really fall in that standard form. Like, which one can I? Okay, so this is actually fine. Let me get the one with numbers. Yeah, like the way this one here is. It's possible that maybe the expression when they give it to you, it's not really 16 here and the x squared. It's possible that it's a whole expression, a whole quadratic expression, such that to work it out, you first complete the square, and in the end, maybe you end up with 16, maybe you end up with 16, and then minus, maybe here you have, it can be, maybe it's x, you can even say plus 3, and then this is squared here. What you have to see is, if the expression reduces to something like this, then you can actually work out this using that sine substitution. But the only thing here is the argument here, this x plus 3, this would have to be what u is, so that the expression now reduces to 16 minus u squared. This would be what is under the square root. So it would be u that you will say to be equals to 4 sine theta. Of course, you know how the rest goes once you reach this stage. So I just wanted to show you guys a trick where you have to first complete the square before you can actually even use that sine substitution. Okay, so any questions there? I'll try to find an example that will actually work with either a sine or cosine substitution that you guys can try to work out from there, where you'd have to first complete the square before you go ahead and finish working out the question. But I think we can actually try to find one. I think I can try to find one. Do you guys want me to find one that we can work out right now all the way to the end? Should I find one right now? Or you guys get how it goes and you can finish it if I give you one? Which is it? Okay, you guys are not responding.
Find one.
Okay. Let's look at this one. Say we have the integral of 1 over, and we have 12 plus 6x minus x squared. And again, we have this integral. So let's focus on the argument here. So what is happening when it comes to that integral there? Well, let's see. Again, we can complete the square here. So if we try to complete the square, we know to say we're going to have, let me get this, x squared plus 6x plus 12. We know this has to be positive, not that minus. So I'll pull out minus 1. So that I have x squared here. And then this becomes minus 6x. This becomes minus 12. I'm completing the square here. So I'll focus on the coefficient of the x term. This becomes minus. This is x squared. So that's minus 6. So first I'll write it exactly the way it is. So minus 6, I'll add half of it. Half of it is minus 3. So half of it squared, I'll add it. Then I'll subtract it, minus 3 squared. Then lastly, that 12 at the end. Once I reach this stage, don't make a mistake of squaring that. You know that, you guys. So you have this. So I'll just get x from here. I'll get minus 3 with its sign there. And then I'll square them. I know that minus 6 is taken care of when I expand this. And then this part now I can expand. I can square me. Minus 3 squared is 9. And then this is minus 12. So when I simplify this, I now have minus 1. And then this is x minus 3 squared. And then this becomes minus. And when I add these two, I get minus 21. When I send that minus inside, now I have minus x minus 3 squared. And this becomes plus 21. So if you look at our integral now, of course, I can rewrite this to 21 minus x minus 3 squared. So when we go back to our integral now becomes 1 over, where we had that expression, that quadratic, we're now going to have this 21 minus x minus 3 squared, then dx. When you look at this expression, if I was just to let u be equals to x minus 3, now it starts to look similar to what we were actually dealing with last time. Because here, of course, if you get du dx, it will be equals to 1, so that dx will just be the same as du. So when I come back to this integral and substitute, what I now have is the integral of 1 over the square root of the 21 remains untouched, then minus, where there is this x minus 3, I'll put u, so it just has to be squared. And then where there is dx right here, we saw dx is just the same as du, so I'll just put du there. So this is what I'm now looking at. And when you look at this expression, you see it looks similar to what we were integrating by using that sine substitution. That sine substitution worked for when you have 1 over the integral of a squared minus x squared dx. We sought to say if this is what you have, then a sine substitution works. That one we saw very well. So the only thing we're seeing here is instead of x, we have u. And our a here is this 21. So we just have to find a way of writing this 21 as something to the power 2. So how can you write 21 as something to the power 2? What must you have? How can I write 20? The root, yes. So it now means that if I wanted to get a out of that 21, I can say 21 will be the same as root 21. Root 21 squared. In other words, our a here is actually equals to root 21. That is what you have to see here. So this is how you would approach it from here. So when you observe this, it now means that our integral is now, I can say 1 over the root of, and I can say root 21 squared, then minus u squared, and then du. At this point, it's exactly what we looked at last night and the night before when we're using that that sine substitution. You know, u will be equals to what? If you want to use sine substitution here, u will be equals to what? By the way, I have to specify, you guys, you don't necessarily have to go through all the trouble of doing this. In most cases, what people would do is they will master how the standard one turns out, the one with a squared and x squared. And then they just identify what your a is. Like here, how we identify that a is actually just root 21. And then they would use this in the integral for this one to predict what the integral for this one would be. That is how most people would actually approach this. But because you guys are doing this for marks, you really don't know where the marks will be given. So you want to still show the steps how you reach to the final answer. But otherwise, you can just know the standard one and then go right ahead from the standard to get the answer. So if you're going from scratch to get the answer, you know to say it's always a sine theta. But our a here is root 21. So this would have to be root 21. And then this would be sine theta. So that if you get the derivative here, d theta, this would just be equals to root 21 and then cos theta. And what I want here is du. So I'll make du subject from this. This would be du will be equals to root 21, then cos theta, d theta. And then we substitute. I'll get this. Now I'll just substitute. In this case, where there's u, I'll put that expression. So where there is u, I'll put root 21. So this is going to be root 21 and then sine theta. But this, remember, is squared because u is squared. Then we have du, and du, we've just seen this is root 21 and then cos theta d theta. And all this is under the root. So if you simplify, you know to say when this comes in, this is going to be, you have that root 21 cos theta, and then this is over the square root of, this is root 21 squared, and this is going to be minus, this is also going to be root 21 squared, then sine squared theta, then d theta here. So it's the same thing, exactly what we're doing. The only thing that makes it weird here is this root 21 and so on. But you know, root 21 is just a here. So you know this is root 21 squared, we can factor it out. So if you factored out root 21 and square it, what is going to come out there? So this is going to come out as root 21 on top, then cos theta. In the denominator, this is going to be the square root of root 21 squared, which is just going to come out as root 21. And then inside the square root, we are going to remain with 1 from here, then minus from this part, we're just going to remain with sine squared theta, then d theta. And you remember that sine squared 1 minus sine squared theta This is the same as cos squared. And the square root of cos squared is sine. Yeah, the square root of cos squared is just cos. This and this will cancel, so that we remain with cos theta here over cos theta here once you square root. So that this is just going to be d theta this side. The cos and the cos will cancel out. Again, we remain with just the square, the integral of d theta. And if we get this, remember how it goes? It's just going to be theta, then plus the constant of integration c. But the only difference here is what is theta. By definition, we said u was equals to root 21, then sine theta. This implies that you have u over root 21, then this is what is equals to sine theta. So that theta will have to be sine inverse of u over root 21. So this is what you bring into this expression. So that now you have, where there's theta, you have sine inverse of u over root 21. Then plus c. But again, what is u? You have to go back and remember what u was from start. U when we started was x minus 3. That was what u was. So you get that x minus 3. Now bring it back where you have u. So the final answer becomes sine inverse. And then you have x minus 3 over root 21, then plus c. So this becomes the final answer. Okay, any questions there?
Can you kindly repeat on how you put is it the u is equals to square root of sine theta?
Okay, so where did that come from? Okay, so it started from here. Started from here. You understand how I reached where this had to be root 21 squared, right?
Yes.
Okay. Okay, so if you text, would you like to Kondwani, let me finish this first, then I'll get back to you. Okay. So the idea here is this. You know the original expression. The original expression is 1 over the square root of a squared minus x. This is the original expression. And you know to say in the original expression, this is x squared. You let x to be equals to whatever is being squared here. This is what comes first, then sine theta. So when I compare this same step to what is here, I see that whatever is being squared here is actually root 21. So in other words, a is actually root 21. But instead of x, what we have is u. So instead of saying x is equals to a sine theta, it's actually u I'm dealing with. But instead of a, what I have is root 21. Everything else is the same. Have I answered that?
Yes.
Konrani, you also have a hand up.
Yes, my question was, what if I root which trig am I supposed to use?
What if?
Let's say I have the integral 1 over 9 minus x squared
without the root.
I use
This one doesn't look like any of the ones we've done. Because if it were tan, you know to say this was supposed to be positive. And if it is cos or sine, then you know this is supposed to be square root. Then for the hyperbolic substitutions, you know to say it's supposed to be x squared minus the number, but they also deal with the square root. So the trick that you'd have to use here, it's not among the ones that we've done. Have you got that?
Yes, I've got it.
Yeah. Okay, so who else has a question? Okay, I think it was just Kononi. Okay. Okay, so now that that is sorted out, we can proceed. Okay. So yeah, I wanted to show you guys that, and we have. So the next thing that we want to look at are integrals that you evaluate by using partial fractions. So let's set the groundwork for those type of integrals. Okay.